Hi there and welcome to my project video. My name is John Murphy and I had dataset 5. Um, we had a single tank problem separated by two different tanks and they're both well mixed and all of that. A lot of the constants are right here. Some assumptions made are listed right here, also listed in the paper above. But I'm just going to walk you through my work mainly. First off, we want to start with the mass balances and establish that QR is going to be equal all across the recycled volumetric flow, and the Q is going to be equal to in and out. Basically, there's no accumulation or loss of liquid. And continuing off of that, we have the energy balances, and that's going to be able to solve. That's going to make us solve for dt1 over dt and d2 over dt, as listed right here. Just doing in minus out and accumulation, but there's not really accumulation. Then we start doing our transfer functions, and this lets us put it in general form and find some general constants that we want for later on for our block diagram, so we can go ahead and move that forward. We do it for both tank 1 and tank 2, solving for k in, k2, tau 1, k1, ks prime, tau 2, and all of that fun stuff. Moving on to the block diagrams, we have a general form of the the block diagrams. We have a response in the middle right here with the process, but just going to go ahead and move through, and this can be simplified down to the GS, or really GP, that is right here. So it's going to be the KS prime over tau prime squared S. It's right there. Sorry, I don't need to list it off really. But you go ahead and go through that. You get our new time constant, our new zeta, our new k value, which is really not used until the fifth part. Then we go ahead and solve for UA, and this is going to be used later on. But we go ahead and solve for, and this is going to be at steady state. So steady state, we don't have any change. We can go ahead and solve for the initial UA. Allows us to find some constants later on and make it as a function of QR. But we found the values for T2 bar and the function for UA for QR, which is going to be right here. This will be delved into later, but I just wanted to find this equation. Then I drop down to the loop diagram. Oh, okay. And I just want to go ahead and reiterate all of my constants. This is more just for me, maybe also helpful for the grader to be able to tell like where I was at. But that made me lead to find that like I need to find kV and tau v. So I go into the next page and I solve for the valve constants and along with the step change in the valve. And that allows me to find the final equation of Ts of t equals to Ts bar plus kVm, 1 minus e to the negative t over tau v. And plugging that into our Excel spreadsheet, this is something completely different right now. This is post change right here. But if we go ahead and look at the steam alone, it shouldn't have changed at all. We have the steam calculated, which would be the same equation listed right here above, with kV, tau v, m, and ts bar. And then we went ahead and used solver to find kV and tau v to just try to minimize the difference between the calculated steam temperature and the measured steam temperature. And we got that under 0.31 or 32. So I mean, it is a pretty good estimate of kV and tau v. Moving on past that, we can go ahead and look at the actual equation for the process. And we split this into three main parts using Heaviside. But three constants here were solved just going through, setting everything, multiplying everything over, and then having three different equations from s squared, s to the first power, and s to the 0th power. Solving for alpha 1, alpha 2, and alpha 3. This allows us to go ahead and split each part into individually Laplace each part. And this is the second part because I want to tackle the hardest part first. So I knew I wanted to be in this final form of b over s minus a squared minus b. And so I went ahead and replaced, I did some square difference, or difference of squares, jeez. Uh, and that allowed me to find a of equal to negative zeta prime over tau prime, and then b equal to square root of zeta prime over tau prime squared minus tau prime squared. And this makes us makes b, we have to assume that b is real, so therefore zeta has to be greater than 1, because if you multiply this tau primes over, then zeta prime squared has to be greater than 1, and therefore zeta prime has to be greater than 1. So therefore we know it's going to be an shoot, I had this listed, sorry. It's going to be an overdamped reaction, right, process. And so once we inverse Laplace that, it's going to be equal to EAT sine hyperbolic sine times BT, and then of course the constant up front because of all the manipulation we had to do. That leaves us alpha 1 and alpha 3, the other two parts, and they were pretty simple, just plug and chug, having to find two new time constants, but that's just because of the nature of the second order process. So once we put it all together, we can find our actual temperature function, and that's going to be the 3 combined inverse Laplaces plus the steady state temperature. And we almost have everything ready. We just have to go ahead and finish the UA part of the problem. And that basically, we want to go ahead and force the top and numerator and denominator to be greater than 0, because UA has to be greater than 0. And the numerator is just going to end up canceling out QRs, so that's not really going to be too helpful. But the denominator has to be greater than 0. And that's going to be pretty important, because we can go ahead and plug in T2 bar, the T2 bar equation that we found from before, and solve for QR. And that's going to have us reach the QR minimum, because this is going to be steady state initial values, and over a while the QR is going to be increasing, theoretically. But it can be held constant because, that's just, it's easier for us. But this is going to be our final equation, the Q times T1 bar minus Tn bar over Ts bar minus T1 bar. And that's going to be, that was ended up being manipulated it ended up being varied. So then once all that was over with and over and done with, I plugged in the actual time or temperature equation and all of the constants as listed right here. And once all those were plugged in, I was able to make it all work, and it actually turned out pretty well. So I have a screenshot of before I started messing with it for the second part of the project, and got a square difference of around 33.2. And this was kind of good to note, because it was a very, very good final estimator of like the final temperatures, but right in the middle, right when like it would overshoot and undershoot just a little bit. And in the long run of things, it really wouldn't matter, because as time went on, and as you had this tank running for quite a while, then it would eventually get at the right temperature. But the intermediate's a little bit janky. So returning back to the work, once we found all of that type of stuff, we had to find the new steady state conditions. And so what was given in the project was that T1 bar is going to be equal to 75 degrees Celsius, and that Q is going to be equal to 500 liters per minute. And so what we can do is just go ahead and plug back in to the Q bar and Tn bar or T1 bar and stuff like that, and it changed everything just a little bit, or not everything a little bit, but a lot of stuff just a little bit. And we can go ahead and get those second design variables right here in the second column. That's going to be in table 1. Yeah, so once we find the new steady state conditions, we can find that by equaling or doing the same energy balances as we did before, setting them equal to 0 and solving for T2. And since we have T1 bar because of the new given information, and Tn bar, we can go ahead and plug and chug for T2 bar and Ts bar, which would be 98.838 and 135.6 degrees Celsius. So here we get the very end. I have just a little bit left. I really didn't understand these units too well, and so I know a lot what I need to study. And so These final parts I didn't really get to finish because I ended up pushing it back a little bit too far and wasn't able to get through everything I needed to. But went through everything I could, try to write down some equations that would be helpful. But at the end of the day, I wasn't really prepared for part 4 and 5. And yeah, that's basically my project. Thank you for watching, and yeah, have a great day.